Carbide burrs, renowned for their durability and metalworking, extend their utility far beyond ferrous and non-ferrous materials into the realms of wood and plastic, where their sharp tungsten carbide flutes enable intricate carving, shaping, and finishing with minimal splintering or melting. For advanced users transitioning from metals, these tools demand nuanced adaptations to accommodate the softer, more fibrous nature of wood and the thermoplastic behaviors of plastics, preventing common pitfalls like charring or gummy residues that can ruin projects. In woodworking, lower rotational speeds, typically 5,000 to 15,000 RPM compared to the 20,000 plus for metals, preserve the material's integrity by reducing frictional heat that scorches delicate grains, while in plastics, fine, shallow cuts at even slower paces, around 3,000 to 10,000 RPM, ensure clean edges without deforming the polymer chains. This article explores these advanced techniques, detailing material-specific adjustments such as flute selection, feed rates, and toolpath strategies, illustrated through conceptual sketches that guide precise execution. Whether crafting custom signage in a Mason, Ohio woodshop or prototyping plastic enclosures for local makerspaces, mastering these methods elevates carbide burrs from basic grinders to versatile sculpting instruments, fostering cleaner results and expanded creative possibilities. In wood applications, advanced carbide burr techniques revolve around harnessing the tool's precision to sculpt organic forms while mitigating the material's tendency to burn or tear under high shear forces, a stark contrast to metal's uniformity. Wood's cellular structure, composed of lignin and cellulose, responds best to burrs with coarser, single-cut flutes for initial roughing, which shear fibers cleanly without compressing them like finer double cuts might, but always at reduced speeds to keep temperatures below 200 degrees Fahrenheit and avoid the acrid smoke of pyrolysis. For instance, when carving intricate reliefs on hardwoods like oak or walnut, sourced from Ohio's abundant timber suppliers, begin with a ball-shaped burr at 8,000 RPM, using light, orbiting passes to hollow concave areas. This adaptation prevents the tool from digging in and splintering end grains, a frequent issue in metals where deeper cuts are tolerable. Material-specific adjustments include pre-treating the wood with a light oil or wax to lubricate the cut and reduce dust inhalation, essential in enclosed garages during masons' humid summers, and selecting burr diameters proportional to detail scale. A 1/8-inch flame burr for fine veining versus a 1/2-inch burr cylindrical for broad surfacing. Feed rate is key. Advance the tool at 1 to 2 inches per second to allow chips to evacuate via the flutes, avoiding clogs that generate localized heat. Imagine a conceptual sketch of the toolpath here. A curved arrow looping in a clockwise spiral from the burr's center outward across a wooden panel's surface, with dashed lines indicating intermittent lifts every 1/4 inch to clear sawdust and cool the interface, visualizing how this path follows the wood's grain direction to minimize tear-out and achieve a feathered edge that blends seamlessly into the surrounding texture. Advanced wood carving extends to multi-layered techniques, such as undercutting for 3D effects or texturing for decorative panels, where burr adaptations emphasize controlled depth and vibration dampening to exploit wood's forgiving compressibility without the rigidity of metals. For softer woods like pine or balsa, often used in Ohio hobbyist projects for lightweight frames, switch to double-cut oval burrs at 5,000 RPM to produce a smoother finish as their crossed flutes shear in multiple directions, reducing the fuzzy edges that single cuts leave on porous grains. This is particularly vital for end grain work, where unchecked speeds above 10,000 RPM can char the exposed cells, creating brittle, discolored zones. Adjustments involve angling the burr at 15 to 30 degrees to the surface for beveling, mimicking hand chisel strokes but with amplified precision, and incorporating pauses every 30 seconds to brush away debris, preventing abrasive recirculation that dulls the carbide edges prematurely. In sculpting a relief carving of a local Mason landmark like the historic Kings Island Archway on basswood, the tree-shaped burr shines for accessing tight crevices, its tapered path allowing undercuts without binding. A sketched illustration might depict a zigzag toolpath descending into a groove, with shaded heat zones fading along the intermittent stops, showing how the Burr's point traces a V-shaped undercut while the base widens the entry, ensuring structural support remains intact, and the wood's natural oils lubricate the cut for extended sessions. Shifting to plastics, advanced carbide burr techniques prioritize ultrafine control to counteract the material's low melting point, often 200 to 300 degrees Fahrenheit for acrylics or polycarbonates, and elasticity, which can lead to melting, cracking, or stringy burrs if approached like metals. Plastics demand the slowest speeds, 3,000 to 8,000 RPM, and the finest double or diamond-cut flutes to minimize heat buildup and achieve burr-free edges, as coarser cuts generate excessive friction that softens the polymer, causing it to weld back onto the tool in a process called galling. For deburring injection-molded parts, common in Ohio's manufacturing scene around Cincinnati, a cone-shaped burr at low speed excels, its tapered form chamfering edges without delaminating layers. Adjustments include using a coolant mist of water or compressed air to evaporate heat instantly, and shallow passes of 0.005 to 0.010 inches to shear cleanly rather than smear. This is crucial for materials like ABS or PVC, where high speeds cause vaporization and toxic fumes. Always vent the workspace, especially in smaller mason home setups. Feed rates slow to 0.5 inches per second allow the flutes to lift molten chips away, preventing remelting. For a plastic enclosure project, such as customizing a 3D printed case for electronics, the cylindrical burr smooths flat surfaces post-printing, but only after annealing the part to relieve stresses that could propagate cracks under burr pressure. In more sophisticated plastic applications, like engraving or contouring thermoform sheets, burr techniques adapt by layering passes with progressive grit refinement, starting with a 1/4-inch ball burr for rough hollowing at 4,000 RPM, then refining with a smaller oval burr to polish without haze. Material-specific tweaks for brittle plastics like acrylic involve a 10-degree tool angle to initiate cuts from the edge inward, reducing chipping, while flexible ones like polyethylene benefit from straight-line paths to avoid stretching. Always test on scrap, as Ohio's variable humidity can alter plastic rigidity. An illustrative sketch for deburring a plastic bracket might show a straight linear toolpath along the edge, with fine serrated lines representing the diamond flute's microcuts, interrupted by cooling arrows spraying mist to dissipate orange heat blobs, contrasting a flawed, circular path that illustrates melting buildup as wavy distortions. For contouring, envision a flowing S-curve path with the flame burr. Dash segments marking liftoff points every 1/8 inch, where the sketch highlights even material removal along radii, ensuring the plastic's transparency remains unscratched for optical applications like signage. Safety and maintenance form the backbone of advanced non-metal burr work, with adjustments like wearing respirators for wood dust, which can cause respiratory issues over time, or nitrile gloves for plastics to avoid static cling of shards. Store burrs in anti-corrosion cases, cleaning flutes with a brass brush after each use to remove resinous buildup. Wood sap hardens quickly while plastic melt sticks tenaciously. In masons' community workshops, where space is at a premium, integrate these techniques with CNC attachments for repeatability, but handheld mastery allows for artistic flair in custom furniture or prototype designs. By dialing in speeds, paths, and flutes to the material's quirks, advanced users unlock carbide burrs' full potential beyond metals, transforming wood and plastic into fluid mediums for innovation. From ornate carvings evoking Ohio's forested heritage to sleek, durable plastic components that withstand everyday rigors.